Welcome to another Explainer. Today, we're diving into the fascinating and, let's be totally honest, sometimes incredibly frustrating world of software maintenance and management. If you've ever wondered why the apps you use literally every single day seem to need constant updates, patches, or complete overhauls, well, you're in the right place.
Let's kick things off with a question that honestly plagues business leaders and developers alike. If software is just code, just a bunch of ones and zeros living on a machine, why does it always seem to need fixing? Unlike a car engine or a refrigerator, there's zero moving parts to grind down over time. So what's actually going on here?
Section 1. The myth of permanent software. To get to the bottom of this, we've got to bust one of the biggest myths out there about digital products, the idea that software is built once and then it just exists permanently in a state of absolute perfection. Yeah, reality is very different. Think about hardware for a second. It follows what engineers call a bathtub curve. Sure, you might have some glitches early on, but then it stabilizes until eventually it just wears out from physical realities. Dust, vibration, temperature extremes. But software doesn't rust. It doesn't physically wear out. Instead, it deteriorates because its environment is constantly shifting. The operating system gets an update, the hardware it runs on evolves, users demand new features, and every single one of those changes introduces the potential for new errors, causing the whole thing to degrade over time.
Section 2. The true cost of change.
And this constant, unavoidable state of flux brings us to a pretty harsh financial reality for any organization trying to keep its digital infrastructure afloat. Get this, a staggering 60 to 70% of all software resources in a typical organization go entirely toward maintenance. Just let that sink in for a second. The vast majority of a software team's time, budget, and brainpower isn't actually spent inventing the next big thing. Nope. It's spent fixing, adapting, and enhancing what has already been built.
There's a brilliant quote from Douglas Adams that perfectly captures this headache. He basically pointed out that when supposedly perfect software breaks, it turns out to be nearly impossible to repair. When software that was deemed flawless on release day suddenly snaps, it is an absolute nightmare to untangle. Because software isn't built with neat, replaceable spare parts like a machine. Fixing a deeply embedded flaw means digging into incredibly complex, abstract logic. And doing that, it can easily trigger a massive cascade of brand new problems.
And that cascade of problems creates a truly explosive cost curve. Consider these numbers. Catch a single critical defect during the initial coding phase. Industry averages show it costs about $1,000 to fix. Not great, but manageable. But if that exact same bug slips through to system testing, the cost rockets up to over $7,000. And if it makes it all the way out into the wild, into post-release maintenance, you're looking at over $14,000 for one single bug. That right there proves exactly why early quality control isn't just a nice-to-have, it's literally vital to a company's financial survival.
Section 3. Legacy systems and evolution.
This escalating cost hits hardest when we talk about older, deeply embedded programs. We call this legacy software. We're talking about systems developed decades ago that are essentially the lifeblood of an enterprise. But because they've been tweaked and modified by dozens of different developers over the years, often with zero documentation, their internal structure is just a fragmented mess. They are incredibly risky to touch, but absolutely indispensable to keeping the lights on. So why not just leave them alone, right? Well, doing nothing just isn't an option. These legacy systems are forced to evolve if they want to survive. They have to adapt to new computing environments, like moving from local servers in a basement up to the cloud. They have to implement entirely new business rules. They have to be stretched to talk to modern web systems. And they constantly need re-architecting just to stay secure in today's highly networked world. The pressure placed on these ancient systems is just immense.
Section 4. Managing the chaos.
Since we know software is guaranteed to change and these legacy systems absolutely have to evolve, the secret isn't pretending change won't happen. It's systematically managing the chaos. And that brings us to software configuration management. Basically, if you don't control change, change is going to control you. Configuration management is the art of tracking and controlling all those modifications. It makes sure that when multiple developers are poking around inside millions of lines of code, they aren't accidentally overwriting each other's work or introducing catastrophic bugs. It is your ultimate defense mechanism.
By strictly following 4 key goals: identifying the exact work products that are going to change, controlling those versions, ensuring the new code is integrated and tested properly, and then reporting those changes to everyone who needs to know, a software team can actually track and manage modifications safely.
Having this kind of structured approach is exactly what prevents that terrifying cascade of unintended, ultra-expensive side effects we talked about a minute ago.
Section 5. Engineering solution.
But what happens when standard maintenance just doesn't cut it anymore? When a legacy system is so incredibly fragmented and unstable that trying to patch it is basically like putting a Band-Aid on a bursting dam. When the underlying architecture itself is failing, we have to pivot our strategy. We move away from software maintenance, which is just correcting and adapting existing code, and step into software re-engineering. This means going in and actually rebuilding the existing system from the ground up to improve its quality, boost its performance, and make sure it can actually be maintained in the future.
There's an analogy here that I absolutely love because it just nails human nature. Re-engineering is a lot like getting your teeth cleaned. You can think of 1,000 reasons to put it off. It takes time, it costs money, so business leaders naturally procrastinate. They delay and delay, trying to squeeze just one more year out of that old system until the software starts causing acute financial pain and operational failure. Just like avoiding the dentist, ignoring the need for re-engineering only guarantees a much more painful and way more expensive intervention down the line.
So how exactly do we pull this off? To effectively save a legacy system, developers follow a very structured process. First, they do an inventory analysis to figure out what they actually have. Then, they restructure the documentation so it actually makes sense. Next up is reverse engineering, basically dissecting all that old messy logic to figure out what it was supposed to do in the first place. After that, they meticulously restructure the code and the data architecture itself. And finally, forward engineering lets them reconstruct the whole thing into a high-quality, modern, maintainable application. It's a massive undertaking for sure, but it is deeply necessary.
Ultimately, the big takeaway here is that software is literally never done. Investing in high quality early on, continuously managing changes to incredibly strict configuration processes, and knowing exactly when it's time to stop patching and start re-engineering, that is what keeps digital products from morphing into massively costly liabilities. Instead, it turns them into the robust engines that drive competitive businesses forward.
I want to leave you with a thought to chew on today. Think about the systems, the apps, and the software driving your own work right at this very moment. Are they built on a solid foundation, ready to evolve with tomorrow's inevitable changes? Or are they fragile legacy systems held together by digital duct tape, just waiting for one wrong update to trigger a total crisis? It's definitely something to consider. Thanks for hanging out with me on this explainer, and keep learning.